Ready, sir.
Ready? Welcome to ACE Online. Myself, Madhusekhar, faculty of ACE Online. I am here going to discuss about the important concepts and some of the expected questions, especially for TS GENCO for triply assistant engineer examination purpose. సో మీకు ఆల్రెడీ తెలుసు రీసెంట్గా ఈ యొక్క ఎలక్ట్రికల్ మెటీరియల్స్ అనే టాపిక్ని ఈ టీఎస్ జెన్కో ఎగ్జామ్లో ఇంట్రడ్యూస్ చేయడం జరిగింది. సో చాలామందికి ఈ యొక్క ఎలక్ట్రికల్ మెటీరియల్స్ అంటే ఏంటి, సిలబస్ ఏంటి, ఎలాంటి క్వశ్చన్స్ అడిగే ఛాన్స్ ఉంది అనే దాని గురించి అపోహలు ఉన్నాయి. సో మీకు ఈ వీడియో ద్వారా మీకు ఒక క్లియర్ కట్ ఐడియా నేను ఇవ్వబోతున్నాను. నౌ ఇఫ్ యు టాక్ అబౌట్ ద TSPSC syllabus, if you talk about the TSPSC syllabus, I'll consider here, I'll explain whatever the IES syllabus is there now for electrical people, IES syllabus, same syllabus was given for you also. మీకు ఐఈఎస్ ట్రిప్లీకి ఏ సిలబస్ అయితే ఉందో సేమ్ సిలబస్ని మీకు ఇక్కడ చేర్చడం జరిగింది. సో ఎలాంటి సిలబస్ అంటే ఇక్కడ లైక్ ఐ విల్ గివ్ యూ ద టాపిక్స్ క్రిస్టలోగ్రఫీ క్వశ్చన్స్. సో ఈ క్రిస్టలోగ్రఫీ నుంచి ఎలాంటి టైప్ ఆఫ్ క్వశ్చన్స్ అడిగే ఛాన్స్ ఉందంటే మీకు like structures, especially the structures like simple cubic structure, body centered cubic structure, face centered cubic structure, hexagonal close packed structure. From these structures there is a chance to ask a question. Okay na? From these structures they will ask you questions, especially from the crystallography. Definitely there is one question, definitely they will ask from these structures. And after that the electrical conductors and semiconductors, okay, electrical conductors, semiconductors. From the conductors they will ask you questions like high resistivity materials, low resistivity materials, factors affecting the resistivity of material, alage Franz-Lorentz law, alage applications of the conductors. So they will ask you from the conductors. Alage semiconductors nunchi types of semiconductors like intrinsic semiconductor, extrinsic semiconductor, like P type, N type semiconductor. With examples they will ask you. And then magnetic materials. From the magnetic materials, different types of magnetic materials they will ask you. Different types of magnetic materials like diamagnetic material, paramagnetic material, ferromagnetic material and antiferromagnetic material, and finally ferrimagnetic material. So from these types of magnetic material definitely there will be one or two questions they will ask you for your exam. Then after that dielectric materials, insulators, okay na, dielectric materials, they are nothing but electrical insulators. Dielectric materials, they are nothing but electrical insulators. From the electrical insulators also they will ask you good number of questions like why are you using glass as an electrical insulator, which material is used to store a charge. So the dielectric materials are used to store a charge and it is also used to store, it is also used as an electrical insulator. So we will see different types of dielectric materials like para-electric material, ferroelectric material and pyroelectric material. And then next they will ask you questions from the ceramics. especially from the ceramics, they will ask you questions, especially structures of ceramics, they will ask you. Structures of ceramics, they will ask you questions. And then superconductors, basic definition, properties of superconductors, they will ask you. Basic definition and properties of superconductors, they will ask you. And then finally, nanomaterials. Nanomaterial is an advanced topic, so there may be or may not be, otherwise if they want to ask a very simple questions, they will ask you. Okay na? Nanomaterials lo nunchi basic definition of nanomaterial or basic questions they will ask you. Superconductors lo nunchi what is superconductor and properties of superconductor, this type of questions they will ask you. So I am expecting for your TS GENCO, I am expecting for your TS GENCO for triple people from this subject 5 to 7 questions. 5 to 7 questions I am expecting from this topic. From this topic, 5 to 7 questions I am expecting. Out of these, the most important topic is crystallography. This is very important topic. Then magnetic materials, this is also very important topic. So there may be chance to ask good number of questions from the crystallography and magnetic materials, and after that maybe from each topic there may be chance to ask one question like that. Okay na? So మీకు TS GENCOలో ఈ టాపిక్స్ ఇవ్వడం జరిగింది. ఈ టాపిక్స్లో నుంచి బేసిక్ ఫండమెంటల్స్ కవర్ చేస్తే సరిపోతుంది. ఓకేనా? బేసిక్ ఫండమెంటల్స్ కవర్ చేస్తే సరిపోతుంది. కట్ Right. So especially from the crystallography, okay, what type of questions they will ask you? So what are the doubts here? Some of the students are asking doubts, so I'll clarify that first. Sir, is class or any other? What is the Hall voltage and Hall voltage coefficient for intrinsic, extrinsic and semiconductor? Remember, the Hall voltage is nothing but it is an effective or resultant voltage between the applied voltage and due to the applied magnetic field. The Hall voltage is different for different semiconductors. For intrinsic semiconductor, Hall voltage is 0. For p-type semiconductor, it is positive, and n-type semiconductor is negative. But Hall voltage coefficient is different. That you will get to know elaborately in our classes. Okay, because of restricted time, I'll explain the important topics, most expected topics I'm going to explain, and expected questions. Suppose if I consider, listen, if I consider crystallography, ఈ యొక్క crystallography నుంచి the most important topic is structures. So I'll give you the table of the structures because I can't able to explain all types of structures at a time here. It takes some 4-5 hours. So I'll give you the table of all 5 types of structure. You just go to the table. Definitely there must be one question from the table. So see here, the table is type of structure, effective number of atoms present inside the unit cell, and the relationship between R and A, and then atomic packing factor. They will ask you atomic packing factor, and coordination number, and finally examples. So from these structures, definitely from these points they will ask you one question. Okay, na? Definitely from these points they will ask you one question. Now see here, the first one, listen carefully, simple cubic structure. In simple cubic structure, 8 atoms are located at 8 corners, so that number of atoms required to form simple cubic structure is 8. And the effective number of atoms are only 1. R and A relation, if I take A is equal to 2R. And atomic packing factor is 0.52. Coordination number is 6. Example is polonium. So this data you should remember. Then the second type of structure is body-centered cubic structure. In body-centered cubic structure, there are 8 atoms at 8 corners. 1 atom is at body center. So total 9 atoms required. And in body-centered cubic structure, the effective number of atoms are 2. And R and A relation is 4R is equal to root 3A. And atomic packing factor is 0.68. Coordination number is 8. Now examples, listen, I'll give a hint of TISCO. TISCO means Tata Iron and Steel Corporation. From this TISCO, I'll give you the examples. The T represent tungsten, I represent iron, S represent sodium, CO represent chromium. Okay, so meeku BCC structure lo direct question like, what is the atomic packing factor of BCC? 0.68. And the relations between lattice constant atomic radius for BCC, 4R is equal to root 3A. And which of the given below are the examples of BCC? So this type of questions they will ask you for each structure. Now if I consider face-centered cubic structure, third one, face-centered cubic structure. In face-centered cubic structure, 8 atoms are located at 8 corners, 6 atoms are located at 6 face center. So the number of atoms required to form this structure is 14. And effective number of atoms present inside the unit cell is 4. And the relationship between R and A is 4R is equal to root 2A. And atomic packing factor is 0.74. Coordination number is 12. Example for the FCC structure. Remember, you are electrical people. For you, the face-centered cubic structure is very, very important. Enduku telusa? All electrical conductors comes under this category, like copper, aluminum, gold, silver, platinum. All these are good conductors. So the structure of these materials are FCC. So there is more chance to ask a question for you, especially from this FCC, right? So copper, aluminum, silver, gold, platinum, nickel, etc. Gold, aluminum, platinum, nickel, etc. Where is gone? Right? Nickel, etc. Right? So for you, FCC structure is very, very important. Okay, na? FCC structure is very, very important. Now the fourth one, if I consider HCP structure, I'll explain after that diamond cubic structure. In HCP structure, the atoms are arranged. There are 12 atoms are arranged at 12 corners of hexagonal unit cell. 2 atoms are arranged at 2 face centers, and 3 atoms are arranged inside the unit cell. So the total number of atoms required here, it is 17. The effective number of atoms are 6. R and A relation is A is equal to 2R is one relation. C by A is equal to 1.634. This is one relation. And atomic packing factor is 0.74. Coordination number is 12. Example for this is cobalt, zinc, cadmium, beryllium, etc. Okay, na? This is the information related to the HCP structure. Next, fifth one is diamond cubic structure. Diamond cubic structure, number of atoms required is 18, because 8 atoms are at 8 corners, 6 atoms are at 6 face centers, 1 atom and 4 atoms are present inside the unit cell and 4 body diagonals. So that 18 atoms required. The effective number of atoms which is 8 atoms, and 8R is equal to root 3A. So atomic packing factor 0.34. Coordination number 4. Diamond is an example. Best example for this structure is diamond, silicon and germanium. So this is the table. From this table, ee table lo nunchi oka question pakka vastundi. I will give you guarantee. So any type of model, like which of the given below is an example of, or the examples of diamond cubic structure, or the relationship between R and A for FCC structure, or the atomic packing factor of BCC. So any type of question they will ask you from these structures, especially for crystallography unit, they will ask you questions from this. This is one of the most important topic, right? So I am going to discuss these important topics or expected questions. So before going to the exam, go through this table. Now, same way for you, magnetic materials also. There are 5 types of magnetic materials. So from these 5 types of magnetic material, definitely there must be one question. So that first I'll frame these 5 types, I'll explain. Then after that, we will see some other important topics. Now, see here, if we talk about types of magnetic materials, I'll give you gist for this. Types of magnetic materials. Okay, na? One is a diamagnetic material, first one. Diamagnetic diamagnetic material, first one. So what is this diamagnetic material? Now see here, in diamagnetic material without any magnetic field, if magnetic field is 0, there is no magnetic dipoles. There is no magnetic dipole. So it don't have any dipoles. Only if we apply the magnetic field, it will generate dipoles. These dipoles we call it as induced dipoles. And these dipoles are interesting. Here some of the dipoles are in opposite direction of the applied field. Remaining large number of dipoles are randomly oriented, like this. Okay? Remember, in which of the given below magnetic material there is no permanent dipoles, that is diamagnetic material. And in diamagnetic material, by applying the field in one direction, the dipoles are aligned in the opposite direction, minor dipoles. So that's why magnetic susceptibility is negative for the diamagnetic material. Very, very important question. For which of the magnetic material the magnetic susceptibility is negative, that is diamagnetic material, straightforward answer. If susceptibility is negative and also it's very small because only minor dipoles are arranged in the opposite direction. So we are familiar mu r is equal to 1 plus susceptibility. So susceptibility is equal to 1 minus mu r if I take, otherwise mu r is equal to 1 plus susceptibility, so that mu r you will get less than 1. Less than 1 you will get for the diamagnetic material. And this diamagnetic material is independent of temperature. At any temperature, it is not going to change. It is independent of temperature. Temperature independent. Temperature independent. And examples of these diamagnetic materials are graphite. Graphite is an example. Silicon is an example. Diamond is an example. Graphite, silicon, diamond, bismuth. These are the examples of diamagnetic material. This is about diamagnetic material. Now, if you talk about paramagnetic material, so one of the students was asking question that will you expect questions from the ESC? Will you expect questions from ESC? One of the student, Sai Kumar, is asking, can we expect this ESC questions directly? Definitely, Sai Kumar. But remember, Sai Kumar, some of the ESC questions are straightforward, easy questions. So they will ask you those questions only. Some of the questions are tricky, lengthy questions are there now. So they may not ask you because you don't have time. Okay, now for ESC high standards required, here it's not required high standard. Simple questions, straightforward questions they will ask you. So in our material we gave level 1 and level 2 questions also. So in ESC level 1 questions if you solve, that is basic questions, that is more than enough. Okay, now in our booklet we have this level 1, level 2. So even if you practice all questions, that will give you advantage to you. You will get information, lot of information, and from that you will guess the answer easily in the exam, GENCO exam. Okay, na Sai Kumar? Right. And Vikram, you are asking another question. Miller indices low negative value to question expect cheyocha. Vikram, general ga Miller indices nunchi question vaste like 100, 101 and 111. Only 3 questions adige chance undi. Okay na, in depth questions adagappochu. So 3 questions lo meeru planes gurtupettukunte saripotundi. 100 plane vachesi square, 101 plane vachesi rectangle, and 111 plane vachesi triangle. If you remember, that is more than enough, Mr. Vikram. Okay na? Okay, definitely I'll give screenshot. Take this screenshot, Vikram. Take this. But I'm having restricted time. Okay, now at least I am expecting today I should explain the structures and types of magnetic materials, because from these regions definitely there must be a chance to ask a question. At least if I cover these two topics, 2 questions you will get. That's why. Okay, na? Diamagnetic material. Next, paramagnetic material. Now listen, if we consider the paramagnetic material have permanent dipoles, but these dipoles are randomly present. There is no order, there is no proper order, but they have permanent dipoles. Only diamagnetic materials do not have permanent dipoles. Now if I apply the magnetic field to this paramagnetic material, some of the dipoles are aligned in the direction of the field, and remaining large dipoles are randomly oriented. Only some minor dipoles are aligned in the direction of the field. Remaining large dipoles are randomly oriented. Okay, now because of this sum of the dipoles, remember, because of this and these dipoles, there is a magnetization that is positive but very small. Susceptibility is small, positive but it's very small. Okay, now positive but it is very small. And if it is positive, relative permeability, that is equal to 1 plus susceptibility, that must be greater than 1. For paramagnetic material, relative permeability greater than 1, susceptibility is positive, and it depends on temperature and follows Curie's law. So Curie's law states that susceptibility C is equal to C by T. So remember, paramagnetic material depends on temperature and follows Curie's law. So susceptibility is equal to C by T. A straightforward question they will ask you, like, which of the given below material follows Curie's law? Paramagnetic material. So Curie's law states that susceptibility is inversely proportional to the temperature. If we increase the temperature, susceptibility is going to decrease. The examples for paramagnetic materials are like air is the best example, sand is the best example, tungsten is the example, titanium is the example. These are some of the examples of para. Okay, but paramagnetic material examples they will not ask, but diamagnetic material examples definitely they will ask. Because diamagnetic material, they are moving away from the strong magnetic field. If we apply the magnetic field, they are moving away from that. So these are the examples, very interesting magnetic characteristics they have, so that meeku ee yokka examples lonchi adige chance undi. Let us see the doubts here. Good evening sir, how many questions are we expecting? See, questions, actually this is the first time they introduced this syllabus kada. So as per my perspective, IES ku vachesi ESC lo manaku 15 questions approximately ఇస్తున్నాడు every year మెటీరియల్ సైన్స్లో నుంచి. సో ఐఎమ్ టేకింగ్ ఆఫ్ ఆఫ్ దట్ 5 to 7 questions I'm expecting from the material science, because first of all, don't think that it is non-technical, it is purely a technical core subject, because here they will ask you questions about electrical materials only. What is the material used in transformer core? Electrical only. What is the material used in overhead electrical wire? Electrical material. So what I am saying, pure electrical materials they will ask you questions. So there is a chance to ask a good number of questions. And direct questions are expecting new subjects, well prepared for new subjects, mainly previous questions. Yes, mostly they will ask you direct questions. Okay, na? Definitely. Right. So this is paramagnetic material. Now listen, the next one is a ferromagnetic material. Ferromagnetic material is very, very important for your exam, because your electrical transformer core is made up of this ferromagnetic material. Electrical transformer core is made up of ferromagnetic material. Example for this is iron, cobalt, nickel, gadolinium and dysprosium. Iron, cobalt, nickel, gadolinium and dysprosium. These examples comes under this ferromagnetic material. జనరలీ ఇఫ్ వీ టేక్ మనం ఒక ఐరన్ పీస్ తీసుకుంటే ఐరన్ అనేది మ్యాగ్నెట్ కాదు. ఎందుకంటే ఆ ఐరన్లో మ్యాగ్నెటిక్ డైపోల్స్ అనేవి ర్యాండమ్గా ఉంటాయి. వన్స్ ఒకసారి మనం మ్యాగ్నెటిక్ ఫీల్డ్ అప్లై చేసినప్పుడు ఐరన్ లోపల ఉండే డైపోల్స్ అనేవి ఒక పర్టికులర్ ఆర్డర్కి వచ్చేస్తాయి. ఆల్ ద డైపోల్స్ ఆర్ గోయింగ్ టు బి అలైన్డ్. సపోజ్ ఏ ఫ్రెష్ ఐరన్ మెటల్ తీసుకుంటే వితౌట్ ఎనీ మ్యాగ్నెటిక్ ఫీల్డ్, ఏ ఫ్రెష్ ఐరన్ మెటల్ తీసుకుంటే నేను ఈ ఫ్రెష్ ఐరన్ మెటల్స్లో మ్యాగ్నెటిక్ డైపోల్స్ అనేవి ర్యాండమ్గా ఉంటాయి. మ్యాగ్నెటిక్ డైపోల్స్ అనేవి ర్యాండమ్గా ఉంటాయి. సో ఇట్ ఈస్ నాట్ ఏ ఫెరోమాగ్నెటిక్ మెటీరియల్. రిమెంబర్, దిస్ ఈజ్ నాట్ ఏ ఫెరోమాగ్నెటిక్ మెటీరియల్. This is not a ferromagnetic material. Now, if I apply the magnetic field in one particular direction, suppose in this direction, all the dipoles are aligned in the same direction. All the dipoles are aligned in the same direction and it reached to the saturation state. Okay, this material reached to the saturation state, final state. It reached to the saturation state. Right. Now, suppose if I remove the magnetic field, iron piece is there. After applying magnetic field, if I remove that, is it material is losing its magnetic power? No, material is not going to lose its magnetic power. So tell me what it is known as. Tell me people, what it is known as. Most of the dipoles are aligned in the same direction. What it is known as, without any magnetic field, it has good amount of magnetization. What it is known as? Tell me, Sai Kumar, Vikram, other people. Tell me what is it is known as? Don't know? Don't know? Retentivity. It is nothing but retentivity. It is the retained magnetic flux present in the material without any electric magnetic field. This is very, very important question. Retentivity. Retentivity is nothing but it is the retained magnetic flux. It is the retained magnetic flux present in the material without any field. Very, very important. Suppose if I apply the magnetic field in opposite direction, at one point all the dipoles are going to be demagnetized. It lost its magnetic power. Tell me what it is known as. Tell me what do you mean by this? What it is known as? What do you mean by this? What do you mean by this? Tell me. What it is known as? If we apply the magnetic field in opposite direction, all the dipoles are randomized and material is demagnetized. That is known as coercivity. Correct, exactly, Razu. This is important. So remember, coercivity. Remember, these two words are very, very important. Retentivity and coercivity. Retentivity and coercivity is very, very important words. Okay, na? These two words are very, very important for your exam. Please go through that. Now, next, another important thing is, ferromagnetic material follows Curie's law. Curie's law, that is susceptibility is equal to C by T minus theta. And at Curie temperature, ferromagnetic material convert into paramagnetic material. Okay, at Curie temperature, the ferromagnetic material convert into paramagnetic material. Do you know what is the Curie temperature of iron? Straightforward question they will ask you. The Curie temperature of iron is, tell me, what is the Curie temperature of iron? What is the Curie temperature of iron? Curie temperature of iron is 7. Curie temperature of iron is 768 degrees Celsius. or 1041 Kelvin. Okay, the Curie temperature of iron is 768 degrees Celsius and 1041 Kelvin. This is very, very, very important. And the ferromagnetic materials follow hysteresis loop behavior, and based on that hysteresis loop behavior, we can understand there are soft and hard magnetic materials. So from this soft and hard magnetic materials also, there is a chance to ask a question. Suppose let us consider, okay, the soft magnetic material is this inner loop. Inner loop is soft magnetic material. Okay, outer loop is hard magnetic material. Inner loop is soft magnetic material. Outer loop is hard magnetic material. So what is soft magnetic material? The soft magnetic material is easily magnetized and easily demagnetized. Soft magnetic material is easily magnetized and easily demagnetized, and this is the retentivity of soft magnetic material. This is the coercivity, retentivity of hard magnetic material. So we can say retentivity of soft magnetic material is low compared to hard magnetic material. Listen, it's a comparison. Right? Coercivity of soft magnetic material is less than hard magnetic material. Right? Suppose soft magnetic material, one application is transformer core. If they ask a question, the properties required to make a transformer core that is made up of soft magnetic material. One option is there, high retentivity. Is it required or not? It required. The transformer core should have high retentivity and low coercivity. Don't think that Sir said here retentivity is low for soft magnetic material and it is made up of transformer core, but it is wrong. You know, transformer core applications point of view, it should have high retentivity and low coercivity. Okay, now it is a comparison in this graph. So most of you people for that question they are confusing. So remember, to make a transformer core, it should have high retentivity and low coercivity. It should have high retentivity and low coercivity. Okay, na? It should have low retentivity, high retentivity and low coercivity. And soft magnetic materials have low hysteresis losses, that is the area of hysteresis loop represent hysteresis loss. Hard magnetic material have more hysteresis losses. But saturation magnetization of hard magnetic material is high. Saturation magnetization of soft magnetic material is low. So this type of questions, so like properties of soft and hard magnetic material. Do you know soft magnetic material, one application you remember, transformer core. Transformer core, one application. For hard magnetic material, you remember permanent magnet. Direct question they will ask you. Direct question, permanent magnet. Direct question they will ask you. The applications of soft magnetic material, a transformer core is made up of soft magnetic material. Right? Here, the permanent magnet is produced by hard magnet. The applications of hard magnet, permanent magnet. Straightforward questions they will ask you from this. Now, another important type of magnetic material is ferrimagnetic material. That is also very, very important. Ferrimagnetic material. Why it is important, you know? For high frequency applications, they will use this one. Ferrimagnetic material. Suppose, let us consider 11 kV volt. To suddenly you want to reduce 440 volts. So high frequency application, this we call it as. So for high frequency transformer core, we are using ferrimagnetic material. Straightforward question. Which of the given below magnetic material is used in high frequency applications? Ferrimagnetic material. What is the reason? Do you know the reason? What are the examples of ferrimagnetic material? You know, the examples of ferrimagnetic materials are spinel structure ceramics, spinel ceramics, spinel structure ceramics. They are like Mn, Fe2O4, Zn, Fe2O4, Ni, Fe2O4, etc. Spinel structure ceramics. They are spinel structure ceramics. The ceramics are electrical insulator na. Ceramics do not have free electrons. They are electrical insulators. So because of this electrical insulating character, the ceramic materials or ferrimagnetic materials do not generate eddy current losses. So eddy current losses are very low for ferrimagnetic materials. Remember, eddy current losses are negligible for ferrimagnetic materials. That's why we are using these materials in high frequency applications. Okay, now the ferrimagnetic materials we are using in high frequency applications because of very low eddy current losses. Very low eddy current losses. That is the main reason. Right? So these are the types of magnetic materials. They will ask you questions. And finally, if we talk about semiconductors, I'll give you a flow chart here. So please go through this flow chart with examples. Semiconductors, if I consider intrinsic semiconductor, compound semiconductor. From this also there is one question compulsory classification: extrinsic, intrinsic, compound and extrinsic semiconductor. Intrinsic semiconductor is a pure form of semiconductor. Example for intrinsic semiconductor is silicon and germanium. Only two examples. Intrinsic semiconductor is a pure form of semiconductor, silicon and germanium. And intrinsic semiconductor, number of holes is equal to number of electrons. And Fermi level is located at middle. Fermi level is located at middle of conduction band and valence band. Remember these points. In case of intrinsic semiconductor, examples are silicon, germanium. Number of electrons equal to number of holes. There is no majority carriers. Fermi level is located at middle. Next, if we talk about compound semiconductor, compound semiconductor, the compound semiconductor is produced by adding third group and fifth group elements. Compound semiconductor is produced by adding third and fifth group elements. Okay, na? Third and fifth group elements, best example is arsenic. Germanium and arsenic is the best example of third group is germanium, arsenic is the fifth group. Suppose if I consider the periodic tables, third group, fourth group and fifth group. Okay, na? Third group, fourth group and fifth group. Nitrogen, phosphorus, arsenic, antimony. Okay, carbon, silicon, germanium, tin. Okay, carbon, silicon, germanium and tin. And boron, aluminum, gallium and boron, aluminum, gallium and tin. Boron, aluminum, gallium and indium. So if you remember these 12 elements, it is easy to find all types of semiconductors. Very important. Compound semiconductor is produced by compounding third group and fifth group. See, best example, gallium and arsenic. Gallium and arsenic is one. Now next is extrinsic semiconductor. It is P type and N type now. P type and N type. Okay. P type semiconductor is produced by adding third group elements with the fourth group elements, or 13th group elements with the 14th group elements. Example, you take boron, silicon, gallium, germanium. Straightforward question they will ask you, what are the doping elements we are going to add for P-type semiconductor? That is boron, aluminum, gallium, indium. Straightforward question. Even in IS also they asked. And what are the elements or doping elements we are going to add for N-type semiconductor? For N-type semiconductor, by adding 5th group elements with the 4th group elements, or 15th group elements with the 14th group elements. For a new periodic table, it is 13, 14, 15. Old periodic table, 3rd, 4th, 5th. Okay, na? So by adding nitrogen, phosphorus, arsenic and antimony, we can make an N-type semiconductor. Remember, by adding nitrogen, suppose I will give you the example of nitrogen and silicon. Okay, arsenic and germanium, these are the examples. Straightforward question. Remember, boron, aluminum, gallium, indium are for the P-type semiconductor. Nitrogen, phosphorus, arsenic and antimony for N-type semiconductor. So these are the different types of semiconductor. From this they will ask you. For P-type semiconductor, the majority carriers are holes, minority carriers are electrons. For N-type semiconductor, majority carriers are electrons and minority carriers are holes. And P-type semiconductor, Fermi level is located near valence band. For M-type semiconductor, Fermi level is located near conduction band. Okay, na? For P-type semiconductor, Fermi level is located near valence band. For N-type semiconductor, Fermi level is located near conduction band. Right? So these are the some of the important topics I covered because of the time constraint. Okay, my focus is actually to cover very important topics. So I discuss structures, important magnetic materials and semiconductors, and most of the questions are theoretical type questions. Most of the questions are very basic theoretical type questions. Now here we are going to start this booster course. So today I am here only and tomorrow heat transfer. Like that, these are the schedules. So you just follow this schedule. Okay. So every day 1 hour we are going to discuss about this important concepts. So by going through these important concepts daily 1 hour, there is more chances to get questions from this. And also pre-recorded videos available in our app. So for especially TS GENCO for 2 months, 3 months, you can avail with a good amount of discount. And we are also going to run this ESC GATE and PSC coaching for 2025. It is going to start again one more batch in July 2nd and 21st, civil, mechanical, electrical, electronics, computer science and data science. And for TS GENCO mock test we are providing. This is very, very important. You know, if you attempt this mock test, it will increase your confidence level. You can understand from where I am doing mistakes, in which field I am very weak. So based on that you can focus more. So definitely you should go through this mock test. And then, so these are the important things related to this, and all the best for you. Okay, na? Right. Thank you.